section 6.2 is on all of the properties again for rational exponents. Now you've seen all of these properties before. Every single one of these, you've seen them before with regular powers for exponents. The only thing that's different is that you're going to look at fractions for the powers instead. First one up here is the product property, a to the m times a to the n. Remember, we add the powers when we see. So in this example here, we've got 5 to the 1/2 times 5 to the 3/2. As long as the base is the same, you never change the base. That is not 5 times 5, 25. You keep the base the same, and you're going to add the powers on the top. 1/2 plus 3/2 is 4/2. Reduce is 5 to the second, and then 25. The next one is the power to a power property. We're going to go backwards. This is the multiply rule right here. A raised to the m times n. This example over here, 3 raised to the 5/2 and then again raised to the second power. We're going to multiply. 5 over 2 times 2 over 1. The 2's will cancel. You're left with 3 to the 5th. And if you can remember your flashcards, 243. A times b raised to the m. This is product. Product to a power. This is the backwards rule. Everything inside the brackets will get raised to that power. A to the m, b to the m. So for this one, we're going to come backwards to each of them. 16 to the 1/2, 9 to the 1/2. Each of these is a doable square root. 4 times 3, 12. Now there is another way that you could do this one. If you choose, and remember you're not going to have a calculator for this piece of the test, 16 times 9, you could multiply that together first, 144, and then to the 1/2. Just be warned that sometimes these numbers might be larger, so you'd be looking at a larger number you might not recognize. This one is not bad, it's 144, and we're looking at the square root of 144. Again, takes you to 12. Next one is the quotient property. Remember, with the product property, we add the powers. Quotient property, we're going to subtract the powers. A raised to the m minus n. And again, that rule, bigger on the top, keep it on the top, subtract from the top down. We're going to use that rule here. 4 to the 5/2, 4 to the 1/2. Again, the base is the same. Do not change the base. And then 5/2 minus 1/2 is 4/2. 4 squared, 16. A to the negative m. Remember, we have the rule with the negative powers. You are never, ever allowed to leave a negative power. You need to flip that. So the phrase that I was asking prior to this chapter was, keep it or flip it. If you see the negative power, you need to flip it to the bottom. 1 is going to be your placeholder on the top, and then it is no longer a negative power. 36 to the negative 1/2. We'll flip it. 1 over 36. It is now raised to the positive 1/2. And that becomes 6. A over b raised to the m, this is just like the product to a power, where we went backwards. You're going to do the same thing here. Go backwards to everything that you see on the inside. This one will be 27 to the 1/3, 64 to the 1/3, 3/4. On this next slide, there's 5 examples here. You may need to, or you may want to, put it on pause. Try these yourself, then turn it back on and see how you did. 12 to the 1/8, 12 to the 5/6. My base matches. Keep the 12. I need to add my powers. All right, now on my example, the first one, it was like denominators. This is not like denominators. So for many of your problems, you're going to have to get a common denominator. For 8 and 6, you could use 24. 1/8 becomes 3 over 24, and then 5/6. This goes into it 4 times. 5 times 4 is 20. 12 raised to the 23 over 24. 5 to the 1/3 times 7 to the 1/4. This is all raised to the 3rd power. These bases do not match. You are not allowed to write 35 here. This is just going to be a backwards with the outside power of raised to the 3. 5 to the 1/3 raised to the 3 times 7 to the 1/4 times 3. The first piece, 5 to the 1/3 times 3 over 1, is just 5 to the first. 7 to the 1/4, and then again raised to the 3rd. We're going to multiply that. 7 to the 3/4. You are not allowed to go any farther. This is not 35 raised to the 3/4. This is done. 2 to the 6th times 4 to the 6th, all raised to the negative 1/6 power. A couple ways we could proceed with this. This again is a product to a power. We can go backwards. 2 raised to the 6 times negative 1/6. That's negative 1. 4 to the 6th raised to the negative 1/6. Multiply here, 6 times negative 1/6. That's 4, again to the negative 1. Each of these, flip it. 1 over 2 to the 1st. 1 over 4 to the 1st. And then multiply. 1/8. That's one way you could do this. The other way you could do this one, since they both have the same power on the inside, you could write it as 2 times 4 to the 6th, and then to the negative 1/6. Since they both share the same power, you are allowed to go backward, put it back together as a product raised to a power. 8 to the 6th to the negative 1/6, and then do your power property. Multiply here, we get 8 to the negative 1. Flip it, 1 over 8. Same thing as we got the other way. 10 over 10 to the 2/5. This is going to be a quotient property, and I'm going to need to subtract my powers, except the 10 doesn't have a power. The only thing I could put there is 10 to the 1st. But again, I don't have a common denominator, so I can't subtract that. So I could change 10 to the 1st into a fraction, same denominator as 5, would become 5/5. Now I have a same denominator. 10 raised to the 5/5 minus 2/5, 3/5, and that doesn't reduce, that's done. 56 to the 1/4, 7 to the 1/4. Do you notice how both of these powers have the same 1/4? I could then write this as 56 over 7, all raised to the 1/4, and then raised to the 5th power. One of the reasons for doing that would be because 56 does divide nicely with 7. I get 8 to the 1/4, and then raised to the 5th. Power says multiply 8 to the 5/4. My son goes to the University of Wisconsin in La Crosse. On the next page, we're looking at the product property for radicals. Both of these two rules can go either forwards or backwards. Well, what does that mean? If I have an nth root of a times b, instead of having one great big radical, I could break it up into two little guys. Nth root of a times the nth root of b. Same thing works with the quotient property. Instead of having one great big radical of the fraction, make it two baby radicals. I could look at just the nth root of a divided by just the nth root of b. Now both of these rules go forwards or backwards. If my problem starts like this, like a fraction, maybe I notice that these two individual numbers might divide nicely, then put it back together as one great big radical of the fraction. So both of these rules go both directions. That's why I put these weird little arrows here. You could go both directions with both of these two rules. Some samples. Cube root of 12 times the cube root of 18. As these two numbers sit, neither one of them is a perfect cube. So instead of two little radicals, let's make one great big radical and try multiplying 12 times 18 together underneath. When I do that, I get 216, and hopefully 216 is one of those numbers you remember. That's a perfect cube. 216 came from 6. And just remember, 216, the cube root of is the same thing as 1/3 power. So there's our number 6. Here's two smaller radicals. Well, neither one of these radicals is a perfect fifth. But what if I make it one giant radical instead and put 96 over 3? That's reducible. 5th root of 32, that's a number we should recognize. 32 to the 1/5 comes from 2. This next one, simplify the cube root of 104. 104 is not a number that we recognize. We've never really dealt with that, which means it's probably able to be broken apart into pieces. So now you need to think about perfect cubes. What are perfect cube numbers? 1, 2 cubed is 8, 3 cubed, 27, 4 cubed, 64. Is one of these numbers possibly a factor of 104? Well, you have to mess around a bit, but you'll find it. Cube root of, I'll go this way, cube root of 8 times the cube root of 13. 8 is my perfect cube. That reduces 2, and then the cube root of 13 does not. That piece that does not will sit in the back. That is my reduced or simplified answer for 104. The next one, we need to simplify the fourth root of 10 over 27. Well, if I make it one great big radical, 10 over 27 doesn't reduce, so that doesn't do me any good. So then, remember the rule, and you can hardly see it on the bottom here. You have to rationalize. You are not allowed to keep radicals in the bottom of a fraction. Usually we talked about multiplying both the top and the bottom by whatever number you see, which would be 27. We could do that. We're just going to get a number that's really large. So we have another option. Could we multiply by just one number that will then take us up to a perfect fourth? So let's think for a second about perfect fourths. These numbers were perfect cubes. Perfect fourths, 1, 2 to the fourth, 16, 3 to the fourth, 81. Does 27 go into 81 nicely? Sure it does. I could multiply 27 times 3 to get me to 81. So instead of multiplying by the entire fourth root of 27, all I really need to do is multiply by the fourth root of 3 on both the top and the bottom. The bottom will then give me the fourth root of 81, which is a perfect fourth. We know that that comes from 3. There I rationalize the bottom. And then do the top. Fourth root of 10 times 3 is 30. And then you just have to think about anything that might reduce out of 30 as a perfect fourth. Well, the only thing that is a perfect fourth is 16. 16 does not go nicely into 30, so I can't reduce that any farther. Right there. Adding and subtracting radicals is not so bad. The one thing you need to make sure is that the index and the base number have to match. It's just like doing like terms. If I were to write this instead of with a radical, if I were to write this as 7x minus, no number here, sneak a 1 in the front, minus 1x, could you do it? Sure, because the variable matches. It would be 6x. This is going to be no different. 7 fifth roots of 12 minus 1 fifth roots of 12 is 6 fifth roots of 12. So if the index, remember the index is this guy sitting in the little box, if the index and the base number both match, you can add and subtract. Well, on this next one, you notice that they don't match, which means you're going to have to do something to reduce. Once you reduce them, you're probably going to get something that matches. So think again about your perfect cubes. We need to find perfect cubes that go into 81. Let me back up a second. Here were my perfect cubes, 1, 8, 27, 64. Does one of those numbers go nicely into 81? Yes, it was 27. So I'm going to break this apart into cube root of 27 times the cube root of 3. 24 has 8 as a factor, so I'll have the cube root of 8 times the cube root of 3. Now I've got a doable piece and a non-doable piece. Cube root of 27 is 3. Cube root of 3, I cannot reduce any farther. Minus cube root of 8 is 2. Cube root of 3 cannot reduce any farther. And now I've got a simplified version. 3 cube roots of 3 minus 2 cube roots of 3. The index and the radical both match, so I can go ahead and subtract. 3 minus 2 is 1. Cube roots of 3. Do I need the 1 in the front? No. Cube root of 3 would be my reduced answer. All right, on this last page, we need to simplify. Cube root of 27, cube root of 27 times q to the 9th. When you have numbers and variables, if you want to, split them apart. Remember, this is what one of our quotient properties with radicals is all about. Instead of one great big radical, write it as two little guys. Cube root of 27 is doable. That's 3. Cube root of q to the 9th. Just remember where this index goes. This index, remember, is the bottom of a fraction. So this really looks like q raised to the 9/3. Since that is reducible, I can write it that way and reduce. Q to the 3rd power. Done. I simplified my radical. Well, what happens if the index does not divide nicely with my power? And that's the case that we see right here. I'll start by doing the number, 28. Square root of 28 has a perfect square in it, 4, 7. X to the 4th. Every even power is reducible. Now remember, there's an invisible, excuse me, there's an invisible little 2 right here. If I put this 2 on the bottom of my fraction, 4/2, that's reducible. So instead of writing the x with the radical, I'm going to write it as 4/2, so you'll see that it's going to reduce. If I do that same thing with both 5 and 3, it doesn't work. So I need to break apart the y into 2 pieces, and I need to break apart the z into 2 pieces, one of which is reducible, and then my leftover. So since I'm dealing with my index of 2, even number, when I break apart y to the 5th, I'm going to go as high as I can up to 5 that will go evenly. Well, the highest I could get would be 4 with 1 left over. So I want to write this as the square root of y to the 4th times the square root of y to the 1st. Everybody agrees that 4 times 1 takes me to the 5 that was there? Do the same thing with z. 1 less than z to the 3rd. Square root of z squared and square root of z to the 1st. Now I have everything that I can in terms of reducing. Square root of 4 reduces. There's 2. We knew that x raised to the 4/2 is x squared. Reduced, reduced. Square root of y to the 4th. Remember your index of 2. Make it under here. That's y squared. Reduced. Jump to the z term. Square root of z squared. My index of 2. Underneath, 2/2 is z to the 1st. Done. And then I have leftovers. All of these leftovers can go underneath one radical. 7yz. And I have simplified the combination number and variables with powers. We're going to be looking at another one that's like this one, numbers with higher powered radicals, to try to simplify, so we will see this again together. All right, and I believe that's your last page. Yes, it is. There's your last page. All right, so now you're going to be going to your practice for 6.2, working with all of your rational exponents. Good luck.